So to introduce, we're going to go right into the webinar here. This webinar is being hosted by ClimateFast. ClimateFast is a grassroots climate action group in the Greater Toronto Area advocating for urgent, meaningful, and equitable action on the climate crisis for over 13 years now. We envision a thriving world where the climate is safe for all living beings and species. Today's webinar is about AI data centers and getting a basic understanding about what they are, how they work, and why they are so energy intensive. Currently in Ontario, there are over 6,500 megawatts of data centers looking to connect, which is equivalent to powering 6.5 million homes. There's a real risk that our electricity bills will go up, our drinking water is put at risk, and greenhouse gas emissions from gas-generated electricity will increase significantly due to these data centers, worsening our climate crisis. In addition, at the local level, residents living near data centers may experience noise pollution, health impacts from on-site diesel generators, which release nitrogen oxide, a harmful pollutant. Data centers in Ontario are getting built and expanded without residents being consulting and respecting treaty rights. We need to pay attention to this issue now before we potentially see similar impacts that we saw happen in Memphis happen here in the GTA. So without further ado, I'm going to present, just give a brief introduction to our guest speakers today. Melika is an AI practitioner with 8 years of experience in data science and machine learning. She spent her career researching, building, and evaluating human-centric intelligent systems for the news, tax, and legal industries while staying mindful of privacy, fairness, and regulatory constraints. She strives to educate non-technical audiences about how new technologies affect their lives and to examine the tech industry through a critical lens. Our second guest speaker, Samir, is a research scientist at the University of Toronto and holds a PhD from the University of British Columbia. His research focuses on interventions for sustaining knowledge production institutions like Wikipedia or local news outlets that have been disrupted by generative AI. He also studies how algorithmic management systems can exacerbate harm to marginalized populations in the labor market. So welcome, Melika and Samir, and I'll hand it off to you to begin the presentations.
Hi, thank you. Can I get a thumbs up if you can see my screen, Anna? Okay, awesome, thanks. Hi, I'm Melika and I'm happy to be here. I'll start with just giving a primer on LLM processing, and then I'll move on to how GPUs fit into that, and then going a little bit into the latest data center and GPU technology and the sort of power consumption and that sort of things. Yeah, let's go for it. So let's take it from the perspective of a single input that we're going to put to an LLM chatbot, right? Let's say I'm going to ask a chatbot, why is my cat fat? This inputs that I put through the chatbot in my phone, it travels through the internet, it gets saved somewhere in cloud storage, which is just sort of another name for like a data center in a remote location that just saves your data. Then it also travels to a GPU cluster or a AI data center for us to actually like process the input and see what we should respond back to this, why is my cat fat? How do we figure that out? The first thing to consider is like computers don't really understand words. The only thing that means anything to them and they can do calculations on is numbers. So the first step is that we need to translate these words into numbers that the computer can then do its math with. Think of this as a secret code dictionary that takes these words and then translates them into numbers that don't really mean anything. It's just sort of like a code. And these numbers that need to like travel through a series of like layers of calculations in totaling like trillions of calculations need to happen on these numbers. And you see these like sort of graphs, or like they call them neural networks. It's sort of like densely connected layers of nodes that represents lots of computations that need to happen. If you've heard deep learning or deep neural networks or neural networks, it's this sort of like dense layers of calculations that need to happen. And we'll get to that, but GPUs are really good at this sort of like layer-wise calculation. So let's get to it. When we talk about like a trillion calculations that need to happen, that is a really big number. That's like 125 times the population of the Earth. So if we gave each person on Earth a tiny calculator that does simple math, we would need like 125 Earths to get a response for just one word that we put in. But maybe we can model this sort of like using the analogy of a sort of like weird soccer field. Let's think about a giant soccer field that doesn't have only like one ball running around. It has like hundreds of balls entering the field at a given time. For each of the words that we input, hundreds of balls are getting kicked into the field one by one. So if we put 5 words, hundreds of balls get entered, then the next set of 100 get entered, and so on. And these balls need to reach the end of this massive soccer field. And another weird thing about this soccer field is that we don't have just one goalpost, we have millions of goalposts. And think of this as sort of like all the possible like responses that you can have in like a dictionary or a language. Like there are so many different things that you could reply with, but only some of those are appropriate to respond back to the query or the input, right? So these balls need to reach just the right goalposts at the very end. But how do we do that? This soccer field is truly massive. Like we'll get to it, but it's gonna represent trillions of calculations. To help these balls get to the end of this field, we have rows over rows over rows of players. So it's not just 11 players as normal soccer. We have like many, like trillions, let's say, players that can do this calculation, like billions. The first set of balls enter the field. They represent the first word that we put in, for example. These players, another thing is weird about these players in this soccer field analogy. The way we can move these players, think of a foosball table where you have a rod and you can move all the players at once with one rotation. So we're gonna rotate this rod once, and that's gonna magically make all these players move the ball forward to the next row. They're gonna kick the ball just a tiny bit, just so it reaches the next set of players. At the same time, the next set of words, the next word is gonna enter in, and that releases another set of balls. So we're gonna move forward, and as long as balls are entering the court, entering the field, players are having to kick it forward one layer at a time. They keep pushing this ball forward just a tiny bit by tiny bit. These represent tiny calculations that need to happen, but there's a lot of them that needs to happen. These balls all together get kicked trillions of times. Trillions of times these balls need to get kicked around till they reach the very end. And depending on how like each of these balls got kicked, each intricate angle that was different with each kick, and multiply that by all the layers of like weird angles that happen in each kick, these balls could end anywhere at the end, right? But these players are so well trained that through all of those kicks, these balls land exactly in the right goals at the very end that we want. So at the end, these balls land into different goals, and we're gonna like tally the balls depending on like which goals they landed and so on. And we're gonna translate this back using that like code dictionary that I talked about. You're gonna translate these numbers back into words and reply back to the user, why is my cat fat? Okay, maybe you spoiled her. But what we just described is a process we call inference, which sort of like means like prediction. And it deals with an already highly trained model or like a highly trained set of players. But before we can put these balls in and expect the right answer at the very end, we need to train our players to how to treat these balls exactly the right way. And that process is called training. How does training happen? During training, you have a coach that puts the team through millions of practice scenarios. When we say practice scenarios, think of this as like millions of books or millions of web pages that were scraped and then like processed and like used as practice runs. So, but the sort of like setting doesn't change. Again, the balls for each practice run, the balls enter the field, the players push it through to the end. But at the very start, they're naive players. They don't know like where they need to kick the ball. So they just randomly like push it around. And at the end, you might just like end up with some gibberish, like instead of like saying, a meaningful response for like, why is my cat fat? You would get something like 72 degrees. It wouldn't make sense. But over time, with millions of practice runs, these like players get to learn exactly how to treat these balls. And that happens through the coach monitoring each of their moves and looking at where the balls landed at the end. Did they land at the right place? If they don't land in the right place, the coach goes back and corrects each player's behavior all the way back to the start. And this is again like, so you did trillions of kicks just to get the balls to the end. You didn't do a good job. Now the coach needs to do trillions of behavior corrections back to the very first layer. And this happens each time for every word that you put in. So imagine how many trillions of kicks need to happen if you process like corpus over corpus, like web page over web page. So many calculations need to happen. That makes the training, phase a very significant source of energy consumption, and it's typically takes like many trial and error. For example, even if you did like all of the web pages, all of the books, you put it through, you practiced on them, at the end you might still have like a really horrible model because you end up realizing your coach wasn't good. So you change your coach and you repeat this process again, which is like another like tons of calculations that need to happen again. So oftentimes like model providers need to like do this over and over again until they find just the right sort of recipe for these kicks that need to happen. But at the end of this, you have these highly trained players that you can just throw any ball at them and they know just how to kick them to get you the right response at the end. Now taking a step back, we want to see how a GPU can help with this sort of problem. Remember, we talked about this sort of like rod behavior where we can control all the players at once. That's a really sort of like special effect that helps us utilize GPUs really well. So GPUs allow us to control like many players at once using this sort of rod. But let's contrast that with a CPU. GPU is a graphics processing unit because it was initially created to help render images on a monitor, and it was fit for sort of like rendering graphics really well. But over time, sort of it was found to be really good at doing crypto processing, and it was found to be really good at the sort of like tiny maths that we want to do, but we want to do a lot of them. GPUs were found to be really good at that too. They weren't initially created for this It was found to be good for that. What the GPU is like a rod that can control like hundreds of players at once. But what the CPU is imagine a rod that can control fewer players, but it can control big players that can push like bigger balls. They can do smaller but more sophisticated smaller number of calculations, but each of those calculations can be really big. That's what a CPU is good at. What a GPU is good at is exactly the kind of math we need. We need lots of like tiny math problems to solve, but we have trillions of them, and GPUs are really good for that. So let's look at like, what does the latest like GPU look like? What is it in real life? Moving back here, you see like the GPUs have like lots of cores in them, and those cores are the number of things we can control at the same time. So the more cores you have, the more players you can control at the same time. So you can imagine if we use the CPU and we can only control like very few players at the same time, the same operation would take much, much longer. That's why GPUs are so popular, because they can help you speed up a lot. So the latest GPU that's available right now is NVIDIA's GB300, otherwise known as Blackwell Ultra. The chip itself on the left-hand side is rather small. It can fit in the palm of your hand, and it has something like 700 cores that can do that sort of like parallel like processing. These GPUs then sit on a tray. Think of this tray as sort of like a flat thing. There are 4 GPUs sitting on this, and this tray then goes inside what we call a rack. It's like sort of like a pillar, and this particular rack contains 18 of these trays. That makes it like 72 GPUs. And power consumption for this rack altogether is 140 kilowatt. Then these racks get placed like stacked together in rows, and they put inside a data center. So in a data center, depending on its size and like when it was built, you would have like sometimes 50 of these, sometimes hundreds of these. Sometimes just like tens of these, but like newer ones built by the hyperscalers, they put a lot of these racks in a given data center. And altogether, it could be like tens of thousands of GPUs. Yeah, the more of these GPUs that you combine, the faster you can calculate, because remember, you can control more players at the same time. So for example, if you combined 50 of these racks, 50 of these pillars, that would mean 7 megawatts. But all of this 7 megawatts is for doing the computations, doing those ball kicks and data transfers and stuff. Cooling, as compared to this, takes much less energy. Talking about cooling, GPUs get really hot because of all those like kicks that need to happen. Things heat up a lot. And the latest GPUs require liquid cooling, like it's built into the GPU setup. Like you can see here, there are like pipes of like hot and cold that go into this tray. Pipe of cold water literally like washes over the GPU, and then the water heats up and goes back out. And then this is a flat tray again, and then at the bottom there is sort of like a digital device that controls how the cooling happens in the rack. And on the right hand side is sort of like bigger pipes coming out of the rack. How do data centers handle liquid cooling? Like it varies quite a lot. Older data centers weren't built for liquid cooling, so they might need something that you'd see on the like right-hand side, where it's sort of like attachments that you attach to a rack that requires liquid cooling, but then it's that attachment allows you to like transfer the heat to the air of the data center, and then you can air cool that out in the traditional way. Or like the newer data centers, the ones more recently built by like Microsoft or XAI, they are built for liquid cooling. So they have like giant pipes coming into the building and then taking the water out. There are various kinds. There's like closed loop and other ways also that like don't add water into the system unless the sort of chemistry of the water changes. I think it's a good time for me to switch to pass it on to Samir.
Okay, cool. Yeah, thank you, Melika. That was amazing. So I want to talk about when the concept of these huge AI data centers even came up, because not so long ago, the best AI models we were using could be run with a single consumer grade GPU rather than a big supercomputer. So I just want to describe how we got from there to here. And then I want to talk about current expert opinions on concerns around increased emissions from AI models. So the first time we saw AI as we currently understand it, as Melika explained it, in the form of models running on GPUs, this is actually quite recent, at least in the history of computing. So only in 2012, it was not for processing text or audio, but rather images. So specifically on this image recognition data set in competition called ImageNet, where you would have these photos with labels, and you would have to develop an image classifier that receives only the image's input, and then you would try to develop this model that like predicts the correct label for it. So the data set was collected in like 2009 at Princeton University. Now, in 2012, we saw the first deep learning model make really big progress on this image recognition task, beating out other models from like top universities and companies by 10%, which is like a fairly large margin in terms of error rates in machine learning. So this model itself was not particularly expensive. It uses GTX 580. I looked this up on eBay earlier this afternoon. Apparently, you can buy this for like, I don't know, like 70 bucks ish. But current top shelf GPUs cost about $30,000 to $40,000 a piece. But this model itself was like this model itself was not particularly useful. There's just like not that many commercial applications for doing really simplistic image labeling of like a jigsaw puzzle in a line. In 2019, I think we saw the first major application of deep learning technology in a commercial context. So specifically for Google search, Google's flagship platform, of course, it was using a model called BERT. And Google released this whole blog post explaining why they made such a drastic change, going from really safe and intuitive keyword search to much more mysterious language models. But still, BERT was a pretty lightweight model. You could run it on a single consumer grade GPU with good speed, maybe set up like a search engine on your laptop. Now, it was only in 2020, so not so long ago, where we saw the emergence of a major AI data center for a single company to train a single model. So specifically, OpenAI had a partnership with Microsoft to help train their GPT-3 model. And they commissioned a major data center for this, going away from a consumer grade like setup to something that's totally out of reach for most people. So specifically, they developed a supercomputer with a ridiculous like 285,000 CPU cores and 10,000 GPUs. So there's a question of like, why did the industry make such like a big jump, so many orders of magnitude here? And the basic intuition that's very prominent in like in R&D in the AI space is this idea that if you want to make your model like twice as good, if you want to cut the error rate in half of some task, what you need to do is roughly double the size of your data set as well as the size of your model. So this idea is extremely prominent and popular. Now, in order to double both these things, you'll need more GPUs to get the processing done. Now, OpenAI didn't just want a model that was like twice as good or as accurate, but they wanted it to be as accurate as possible, subject to like physical limitations. So they didn't just go from like 16 GPUs like BERT had used to like 32 GPUs, but rather from 16 to 10,000. So to put this in context, like BERT was trained on about 7,000 books worth of text data, but GPT-3 was trained on 400 times as much as that, which was already a lot. And the model itself was also 340 times larger. So there's absolutely no way you could load this on even the most expensive like consumer grade laptop you can find on the market. Yeah, and that's kind of when we saw the first major AI data center. And of course, in 2022, you had the release of GPT 3.5, otherwise known as ChatGPT, which really ignited this AI data center craze. So there's a question of whether the like of with all these AI data centers cropping up all over, whether this is going to increase carbon emissions. And the answer is yes, almost certainly, like practically certainly. And this is primarily going to come, of course, from increased electricity demand. So this Wired investigative report argues that the U.S. is poised to see an electricity demand increase from 60 to 80% through 2050, and data centers alone are projected to make up about half of this. And so this increase in electricity demand will, of course, be fueled in part by an increase in carbon emissions. So again, as this report says, that with attacks on renewable energy being embedded into regulatory regimes and few significant national policies restricting carbon emissions from power plants, we can see a 19 and 29% increase in carbon emissions. Now, we don't have to rely on projections. We can also look at recent increases in emissions from hyperscalers. So Google's overall emissions have risen 51% compared with the 2019 baseline. Microsoft's overall carbon footprint has increased by more than 23% since 2020. Sorry, I should say 2024. And Amazon's have increased by 6% in 2024 after previous 2 years of declines. We also see, just like following discourse around these things, that Google has removed their net zero pledge from their sustainability website. So there's a question of whether the AI industry on its own will develop more efficient tooling and thus reduce these carbon emission projections. And there's decent reason to be somewhat optimistic about this, but also considerable reasons to be skeptical about it as well. So just like looking at it from both sides, there's some precedent for these models becoming more efficient. So like GPT-4o released after GPT-4 was significantly faster, cheaper, and smaller than GPT-4. However, we also need to account for this paradox, famously known as Jamon's paradox in economics. This is the idea when resources get more efficient, they also get a lot more usage. They become cheaper, so there's more demand for it. You can directly see this right now. So with organizations, companies doing workflows with like AI, quote unquote AI agents, where the inputs to the model are not just like people texting with ChatGPT, but rather you might have a model that's looking at thousands of source code files or working with screenshots of a web browser. And again, processing lots of screenshots, lots of images is a lot more intensive than responding to like text messages that you send to ChatGPT. And more broadly, you can see the industry going towards more intensive computational tasks. So you can see this in like big acquisitions that major industry players have made. So if I have a basic sentence like on the right here, if I entered a text version into a model versus if I like spoke it to the speech version of that same model, the spoken version is likely to be at least 25 times more computationally intensive than the written version. And of course, this gets significantly worse if we're talking about video processing, which some organizations are also working on. So broadly, I don't think that there's there's not super strong empirically sound reasoning to suggest that the industry will become like substantially more efficient over the years. I think there is good reason to actually expect the opposite. So yeah, that's all I want to say. I'll pass it off to Anna. Thanks.
Okay, where did the slides go? One second. Am I supposed to share from here or?
Oh, I can keep sharing.
Oh, okay, perfect. Okay, so the status of data centers in Ontario. So currently there are, according to datacenters.com, 110 data centers in Ontario. As of December 2025 in Ontario, if you go back,
Sorry.
there was over 6,500 megawatts of new data centers looking to connect to Ontario's grid. And this number is increasing rapidly as we speak. So for context on how big 6,500 megawatts is, it's equivalent to about powering 6.5 million homes, or about a third of Ontario's electricity demand during peak. And right now, politicians are being lobbied by data center companies as we speak. We know this because this has been mentioned by the politicians themselves. And some of us who were involved in November in writing to the Minister of Energy and Mines and whatnot. There was the passing of Bill 40 that happened recently in December 2025. Following that, we're not certain how data centers are going to be selected and what criteria they're going to use, but that's currently in development at the Ministry of Energy and Mines, and I believe also the Ontario Energy Board too. Next slide. Okay, so just for context on how quickly things are growing, so in June 2025, there were 12 active applicants, so data centers, trying to connect to the grid, demanding about 2,327 megawatts worth of electricity from in Ontario specifically. And then by December, we have this number, 6,500 megawatts. That's about a 3 times increase almost between a 7-month period. And we don't know how quickly or what rate it will grow into 2026. Next slide. Where are they? There are different websites that you can check out that exist right now, and see where they are. But obviously, some data centers are a lot larger than others. And we're doing a thorough analysis of which ones have documented levels of nitrogen oxide, because those are the really big and serious ones. So those are starred here just for reference. This is not a complete list. The one in Richmond Hill at the top here is like in progress, and we don't have a lot of information on it, but that's one to really keep an eye out on. But the other stars, which are more like south, those ones are already existing ones, and they do produce nitrogen oxide. I put it in purple, the really big ones. Like those ones, I don't think have media coverage, and have really big carbon impact. So those are ones to look into. And the one that most people are probably familiar with is the big Microsoft one that's in construction right now and almost done. The Microsoft one, that's in the middle here in Etobicoke, right near the highway. So we probably want to start looking into those. Next slide. And yeah, next step. There's a really, really long list of next steps, but just to highlight a couple, right now, between now and March 23rd, the Ontario legislature is closed, but on March 23rd, it opens up again. So there can be actions done between now and then. And right now, the Ministry of Energy and Mines, as I mentioned, is coming up with their criteria for how to prioritize or select data centers. And you can email them using this data.center.consultation@ontario.ca to let them know your thoughts. And I would highlight, putting in that email a request to meet with them on behalf of your climate group, and they might actually meet with you. That was our case. We were able to meet with them. So this might be a way to actually get a hold of the public service side of things. The second thing is just contact your local municipality. Ask your counselor if there's anything happening in your ward. That is probably the most high impact thing you could do, is looking at zoning changes for existing and potentially new data centers. We have a public resource folder where we share community resources. And so if you want to add more to this folder, or you want to check out what we have there, there's quite a bit to see. So there's that. And then the last thing here is, if you work in tech or want to learn about like unionizing and like finding like-minded people in tech who are working on I guess like building worker power and such. There are two groups here, Tech Workers Coalition and Technologists for Democracy. So they're going to speak briefly about some of the things that they're doing and how to get involved. So I'll pass it off to Andrew, who's from Tech Workers for Coalition.
Hey, good evening, everyone. Can you all hear me? Perfect. All right. Out of curiosity, if you can just put in the chat, just put a, I don't know, Y, like the letter Y if you work in tech. I'm just kind of curious if we have any who are joining us. And if not, that's okay. Because you don't need to be in tech to talk about, for me to understand what it is I'm talking about. Welcome. All right, so I'm here to speak to you on behalf of the Tech Workers Coalition, which is a rank and file worker-led coalition of workers in around the tech industry, labor organizers, community organizers, and friends that are, it's a global organization, but I'm speaking on behalf of the Canadian chapter, where we really are working in solidarity with existing movements, mostly to build rank and file worker power in tech. And so what does this really mean? What this means is we believe in building solidarity and class consciousness amongst tech workers. We believe in developing worker labor leaders, and we believe in organizing across job functions for wall-to-wall unions. Whether you're a software engineer, product manager, customer success manager, drive an Uber, if you work in a tech company, you're generating value for these tech companies. So, you know, this is kind of the stance Tech Workers Coalition takes with regards to tech. So you might be wondering, what does labor have to do with kind of the climate justice things that we're talking about here and data centers? Well, I would submit to you that we've heard about how Microsoft, Amazon are the ones building data centers, NVIDIA, Amazon, Meta, and most of these decisions are being driven by management, senior management at these companies, the C-suite. But there's also people, and I would submit that I think a very under-leveraged and underexplored area in which we can actually challenge some of these decisions. Obviously we should definitely lobby and call our MPs and do all that kind of advocacy. But I would submit that worker organizing is one way in which we can do that. And this isn't just a theoretical exercise. It has actually happened. Through the Tech Workers Coalition, not the Canadian chapter, more in the United States. But it is meant to be a political home where many workers have formed movements to build worker power necessary to contest some of these decisions where they disagree with what their bosses are doing. And a good example of that is Amazon, one of the biggest builders of these data centers. Amazon employees formed Amazon Employees for Climate Justice. They've organized internally to challenge Amazon's claims of trying to be carbon neutral by 2040. No one really believes Amazon's going to be carbon neutral by 2040. In 2023, they organized a walkout of over 2,000 Amazon workers protesting the company's failure to honor their own self-professed climate pledge. In November of last year, they released an open letter campaign that rightfully connects the climate crisis that Amazon's data center build-out is doing with their own job security, knowing that AI is actually being used to displace many of the people who work within Amazon. And actually today, Amazon just announced layoffs of 16,000 employees at all levels, whether you work in software or in warehouses. That walkout was really inspiring because it was actually wall to wall where you had software engineers walking out together in solidarity with warehouse workers. So that was really, really cool. It's not just the workplace too, as we all know. We might work at a tech company, but we still live in community. One of the most successful oppositions to data centers happened in Tucson, Arizona, where we had Tech Worker Coalition members opposing Project Blue, which is an AWS data center build out in Tucson, Arizona. It has kind of stalled, and I will say, like, where there was some early success, it sounds like City Council does intend to move forward with that data center build out. But that being said, I do think that Ontario has a lot to learn in other places, and I think Tucson's a pretty promising place where TWC has had a bit of a footprint to do it. So really, what we're trying to do here at Tech Workers Coalition is organize tech workers as a counterweight to tech CEOs who have shown that they make decisions that aren't exactly pro-society. So really inviting you all to let Tech Workers Coalition be one of your political homes to build the power of workers to have agency over the technologies we build and deploy. I'm very well aware that the odds are always stacked against workers, like the risk of getting fired and being retaliated against is real, but the ability to actually enact change is quite high. And I'm here to tell you it can be done. I'm a union steward for a 100% remote tech company where I was part of remotely organizing and winning recognition and a collectively bargained agreement with a 100% remote tech company affiliated with OPEIU 153. I'm here to tell you that tech workers can organize their workplaces. We've done a lot of workplace organizing around things like having AI be used for our performance reviews, which, as you know, in tech work, if some of you have ever had to do stack ranking, you know that's actually a big win that you can do where workers actually have the power, where management kind of really doesn't have a choice. So at least the Canadian chapter, we have a weekly virtual coffee, which I encourage you all to join, and many upcoming events from book clubs to solidarity campaigns. I'm going to drop a couple of links in the chat. I see a couple of people have dropped some links. We have a website, we have an email. We do ask people if they would like to join. We vet them just to make sure that they aren't, bosses or whatever. And I'll also share some of the campaigns that Amazon Employees for Climate Justice has been doing, but also some of the work that Tech Workers Coalition has been doing to organize around how AI is being deployed in the workplace. Because ultimately, the reason these data centers are being built is in service to this technology, this artificial intelligence technology. So I'm just going to drop a couple of links. I've talked long enough, so I'll pass it over to our colleagues at Technologists for Democracy, who we collaborate with quite often. So.
Okay, let's see. Adam, are you here, Adam? Okay, I think Adam, there is an Adam. Okay, I'm here, can't enable my mic. Oh, okay, I think you might need to request. I'll make you co-host. Okay, try now.
Hi there. Can you hear me?
Yes.
Awesome. Great. I'll quickly share my screen. I won't take over too much time. So I just wanted to do a quick overview of Technologists for Democracy, and thank you, Andrew, for your presentation on the Tech Workers Coalition. I'm a tech worker myself. It's very inspiring to hear about these things. And so yeah, in the same vein as I guess Tech Workers Coalition. We're Technologists for Democracy. We're different in that we don't organize. However, we are a more advocacy side of we're more public advocacy organization that runs campaigns on particularly controversial issues such as data privacy incursions or data censors and a bunch of other issues that we would like to expand on, because the name Technologists for Democracy means it's an umbrella term. It can mean a whole host of things that matter to people all around. And so just a quick overview of our goals and values. Starting off with our goals, we want to act as a watchdog. We want to make sure that companies aren't just allowed to breeze through unethical violations of personal privacy or create these data centers that are just destroying the environment around the communities. We want to make sure that there's public pressure around these issues, and that there's also an educated consensus around these issues too, which is also why we want to have some technical expertise for public education on these tech policy issues. These tech policy issues are very complicated because the technology itself is complicated. And so it's no surprise that a lot of people always need a refresher on what GPUs are, what CPUs are, and so many things, because yeah, it takes a degree to understand these things properly. We also want to nudge tech culture. A lot of tech culture is dominated by your traditional corporate infrastructure. A lot of tech is also behind paywalls or in closed ecosystems where you have to own an iPhone to have access to a bunch of things. We want to make sure that we move towards a more open tech space where some things are more shared and more community driven. And so this is also another reason why the democracy also matters to us. And we want to also protect and strengthen democracy through all these things. Ideally, this is the end goal. And so our values are decentralization. We want to make sure that every part of a community is involved. At the end of the day, it's not just us technologists that use technology and create technology. At the end of the day, it's you, because you're the data that is sometimes fed into these large language models. So they are what you provide them as well. So you create these things, and so it's also on you to talk about these things and make sure that your voice is heard on how this technology evolves. We want to make sure that we want to strive for equity. We want to make sure that all underrepresented groups are given a space for proper discussion and consultation, because as we all know, there's a big issue on marginalized communities not being adequately represented, especially in data, which makes it very difficult for proper and adequate results to come out from these models. We want to also make sure that there's some kind of local democracy. At the end of the day, localities know themselves best. We don't want to have one node impose their will over another community, and so we want to make sure that multiple people empower themselves and empower other people too to take up these issues. And we want to also strive for radical openness. All our documents are commentable by default, and so yeah, we want to make sure that everyone is able to access our what we do in our work, and that we also don't want to hide anything, because at the end of the day, it's open to everyone. So just to give you an idea, these are our campaigns that we led. We had a self-driving delivery campaign that was mentioned in global news. We were able to mention this issue to City Hall and then eventually get news coverage on that. Yours truly was able to get a spot on a podcast about digital ad billboards and concourses. So if you get the right people to talk about these issues, it can go very far. And so that's what we also want to do, is build a base of power in a way where we can reach the right journalists, we can reach the right people, the right policy experts, to make sure that that our campaigns are heard as far and wide as possible. And then just to make sure that you know where to find us, this is our website, techfordemocracy.ca. We still don't have our own channels or servers just yet. And since we were created as part of Civic Tech Toronto, we have our Slack channel within Civic Tech Toronto. So you can visit civictech.ca and find a Slack button at the top right of the website. And from there, you can just join Proj TFD. And so yeah, I'll also put my email address in the chat in case anyone wants to join in from email. And also Mel, who was presenting, is part of Technologists for Democracy. So it's awesome. Anyways, thanks, Anna.
Thanks, Adam. That's very informative. And I think Andrew had to drop off, but hopefully this gives a little bit of a taste into different groups, especially in the tech world. If you work in it, there are things happening and groups to join and get involved.